defend decisions with geotextile filter design. I'll do so with regard to what I might call the rules of engagement. What kind of choices do we have for decision support tools for geotextile filter design? I'm going to acknowledge one or two field examples. And along the way, I'd like to also connect it into the nature and the origin of granular filter design as well. And that way we can place in context, and perhaps that's the key learning objective, is to place in context, almost to draw parallels between, hey, if this is how I'm doing it with geotextile filters, how would I be doing it with a granular filter? And where are the schools of thought with regard to defensible practice, and where might you put your greatest focused effort? When might it be suitable or appropriate to support your decisions with complementary lab tests? And I've worked on projects where all those avenues have been explored, and I'll try to place in the context of the state of the practice both its evolution and the role of the role of case precedent. That might be the best way of putting it. If the mechanics of the reinforced soil are rather prescriptive and tend to lead to converging kinds of paths of decision making, it's a little bit more open. I wouldn't describe it as the Wild West, but it's a little bit more open with the geotextile filters. So those are my preambles, and the learning objectives are to recognize the duality, the parallel world of the granular filters. So, and recall that last week I gave out homework assignment number 2, and I'll make a couple of comments about that as well. Now, may I ask you if you have any opening questions yourselves? Then by all means, let me invite you, if you've got any questions of clarification, anything that you would you'd like to explore in advance of me opening up this lecture, please go ahead and either unmute yourselves or raise a hand, and I'd be delighted to entertain any opening remarks that you may have too. I'll pause momentarily, and that's looking pretty good. Okay, then informed by that, let's move to recognize this world of the geotextile and the granular. I'm going to just pick up on something I mentioned at the end of the previous lecture. I spoke of a South African viewpoint. I've extracted this, I just pulled it off last night. Geotechnical News, the magazine of the Canadian Geotechnical Society, March 2015, wrote or carried an article that Kelvin Legg wrote. Oh, you know what? Let me start the recording. I think I might have to pop into here.
This meeting is being recorded.
Wonderful. Thank you. Okay. So Kelvin, a very nice individual. I've met him on a number of occasions professionally. And Kelvin wrote an article. I guess he had been tasked with the South African National Committee on Large Dams, so kind of the South African chapter, if you want to call it, of ICOLD, with revisiting filter design practice. ICOLD had a now very dated document on geotextile filters and dams. Culturally, it tended to park them as a relatively new material. Perhaps at the time of writing that was true, but giving, as Kelvin wrote, giving recognition to the importance of competent filters, and that's very true in dam engineering. It's probably the critical component. The prevalence of failures arising from internal erosion of the dam, internal erosion of granular filters, was perhaps most novel intended contribution of the current version of the Sancold draft. So Sancold was drafting. I checked to see if anything had come from this, and I couldn't find anything myself last night, but it was a bit of a cursory check. Perhaps the most novel intended contribution of Sancold's revisiting thing is the concept of a composite filter. And this is what I wanted to pick up on. Does it have to be a geotextile filter, or at the exclusion of a geotextile, should it be a granular filter, or could it be both, in fact? Where the proven compatibility allows for geotextile as an adjunct. And that's careful wording. It's intended to complement the granular filter. And it provides some observations there. So that would be worth just keeping an eye on. I might even drop Kelvin an email and check in with him. I've stayed with him actually in the past, and check in with him and just see what came of that initiative. Okay. So I don't want it to make it sound like it's granular or geotextile. That very nicely articulated the concept of a geotextile filter as an adjunct to a dam. And I say that because there are articles written, I've pulled up one or two here, Geosynthetic Systems for Earth Dams, 35 years of experience, and this article in Geotextiles and Geomembranes, written by Yves Foray, who was very knowledgeable, I'm sure he's retired now, on filter design, but analysis of the geotextile filter at Valcross Dam, which is in France, and after 21 years of service, and materials were exhumed and looked at. So that I raise those two. We'll visit them a little bit. But I raise those issues because when it comes to the last lecture on durability of geosynthetics, it's my intent to speak to durability of geogrids in reinforced soil with regard to a case study of exhuming materials. It's my intent to speak to geotextiles in earth dams and do so with regard to the Valcross Dam. I've actually visited, I've had the privilege of visiting Valcross Dam. And then I have an article on barrier systems and the durability of geomembranes in barrier systems. So there's a little bit of spillover from the wall applications, from the filtration applications, and from the barrier applications to the geomembranes. So there's our philosophical approach, and let me knit this in a little bit to the current assignment, were I to give a little bit of a note to that. Recall that the assignment, which is looking at this combination of either a granular or a geotextile filter. So the first part is relating to granular filters. The second part is relating to geotextile filters. The third part is relating to lab testing protocols, either for a granular filter, the Foster-Fell approach, or a geotextile filter, the ASTM approach. The Foster-Fell is not a standardized test. The gradient ratio and the hydraulic conductivity are. So this is spanning across, And it's not just a matter, and please, it's a part of the learning objectives almost. It's not just looking at, hey, how is this soil retention done, right? But also what is the basis for the design practice, and to go in and actually not blindly apply something, but to try and inform yourself on the origins of an empirical rule for soil retention, and the origins of empirical rules for soil retention. So I'll return to this, but moving forward in the main part of the lecture notes. Let me speak to this. This is an attempt that I've made to capture the decisions that we need to take and defend for granular filters. Ultimately, it ends up with a consideration of permeability, a consideration of base soil retention. That's often what we might think of in granular filter design, and Terzagh's rules for certain categories of base soil, but the D15, D85 rule for base soil retention, and a similar empirical rule for permeability. And that's what we tend to think about as kind of the two cornerstones of granular filter design. And that's very true. It exerts an influence and is captured in two, for example, in two of the control points. There are 7 control points. I think I captured that here. Yes, the corresponding gradation limits for a candidate granular filter are specified with reference to 7 control points. And permeability is one of those, and base soil retention is another one. And then beyond that, in the world of granular filters, we have concern for the potential that it segregates, especially during placement, but perhaps during transport as well as placement. Our granular filter is not a nice uniform mix of materials, but the large particles separate out, and the smaller ones likewise. This world of internal stability is also another one that has gained considerable attention. I think to tell you the truth, as a degree of honesty, has swept the interpretation of performance monitoring, and as a series of case study incidents have been acknowledged, reported, disseminated, and discussed. And in fact, I see, for example, what has really captured the world of the internal stability would be the ICOLD Bulletin 164, which came out about, I think officially, maybe about 4 years or so ago. And that was a document really intended to guide practitioners on how to address concerns for internal instability, that seepage through the earth dam or its foundation may pick up and selectively erode a finer fraction of zoned materials in the dam or indeed in its foundation, and that this could lead to piping and sinkhole activity. And it could be not explicitly taken account of in filter design, but concern that perhaps the mineralogy of the filter might lead it to be susceptible to grain crushing. I'm going to call that a placement and durability issue, whether or not you may suffer because perhaps, for example, you have a presence of carbonate minerals in the parent rock that you in the source rock for the borrow source materials, be those in this part of the world at least glacially derived materials. But might the granular filter be susceptible to grain crushing or particle breakage? Is that going to generate an adverse fines content? might that fines content compromise permeability a little bit? Or more to the point, might that fines content lead to any potential for fracturing? Might it assist with any susceptibility to hydraulic fracture, for example? Especially when you think that the filters may be there and with water seepage through them and little potential for cementation at particle contacts and so on. So that's a world that I'm going to capture these ones in highlighted yellow, because ultimately the permeability, the base soil retention, internal stability, which really, to tell you the truth, is looking. Actually, I'm not going to highlight the gap graded, because we can have broadly graded soils that have a long tail that can also be susceptible to internal instability. But let's argue the case that these 4 highlighted boxes will map onto control points, 7 in total, that govern the gradation envelope of a granular filter. Okay, and you'll see that in the homework assignment. Now, were I to draw the parallels across to the geotextiles, then first of all, perhaps we see, where have some of the boxes gone? We see that, yes, base soil retention is important, clearly. Yes, we see that permeability is important. We don't want to be impeding the cross-plane flow of water through, or indeed on occasionally within, the geotextile. We could argue perhaps that there are parallels for placement and durability in terms of installation and durability. But the third criterion that pops up for the geotextile filter is tensile strength. And of course, that's not appearing over here in the filter, the granular filter, because a granular filter won't have tensile strength. And in fact, if anything, we don't really want that much tensile strength in case, again, it leads to this potential for hydraulic fracture. Notice also that everything in the gray area, an unfortunate term, but this gray area of segregation and internal stability, we don't have to concern ourselves quite so much. Let's say this is an integrity issue, integrity of the granular filter in terms of its pore structure, perhaps. And we don't have to worry that much about the integrity of the pore structure of the geotextile, maybe ironically because it has tensile strength and it holds its integrity through that attribute of the material. So I want to leave this. I want to leave this page with almost a mind map, if you will, of the manner in which. In fact, here's another perhaps interesting take. By and large, you're going to try and source your parent material for the filter as close to your project as possible. And then you fabricate your filter on site, arguably. I'm thinking of dams, for example. So in contrast to sourcing the material as close to the dam site and fabricating the filter on site, with a geotextile, you source and fabricate the geotextile off-site and then deliver it. In fact, you fabricate it under, one would expect, very well controlled conditions. And in fact, statistically, you've got roll upon roll upon roll coming off the manufacturing facility, being tested at source, statistical values on opening size, which will control base soil retention and to a large extent permeability. Statistical testing for tensile strength. So there are interesting facets when we start to look at kind of the two materials side by side. Okay, now if I again map a little bit back to the homework assignment. It's this National Engineering Handbook, this NEH Chapter 26, that is the source document to go to for filter design. It's got the 7 control points. One of those control points is for soil retention. So in assignment number 2, arguably you're looking at this. The assignment number 2 on soil retention, and in it you would go in the granular filter design. You have to categorize the base soil with the NEH Chapter 26 approach into one of 4 base soil categories, from very fine to very coarse. And it transpires that for the assignment, the categorization that you treat the core of the Curzio Dam is a category 2 base soil, and that category 2 base soil yields an empirical rule for soil retention. D15 of the filter must be less than or equal to some value, 0.7 of a millimeter, and so my question is, or at least as a part of the learning objective of how the assignment and the lecture interweave, we're about to go through with a fine-tooth comb and look at where all of these empirical rules or criteria are coming for geotextile filters. But where does it come from for the base soil retention? Where are the origins of this empiricism? Because over here on the base soil retention, we may expect to find empirical rules, for example, that might have an O95, a 95th percentage opening size. So here it's an opening size, here it's a grain size, really as a surrogate for an opening size. And we might expect empirical criteria that says O95 must be less than a certain particle size. Let me show you this geotextile. And actually you can see from the manufacturing, do you see those? These distinct, those are probably the largest opening sizes here. It's coming from the needle punching. You could, those are where as part of the manufacturing process. And this is actually the geotextile from the Valcross Dam. And so we want the larger of those opening sizes to be smaller than some representative grain size of the base soil. O95 of the filter, and this would be D15 of the filter. Maybe I won't put a little subscript for that. But you see the parallels, and we're about to ask ourselves, how reasonable is it to have some confidence in this value? We're going to examine the origins of this, and it's instructive to examine the origins of the base soil retention. Okay, and so that's why I ask you in the homework assignment, with reference to the literature, cite the evidence in support of this empirical rule D15 max, less than 0.7 of a millimeter. Let me put here, because it will be D15, let's say max, less than, in this case, 0.7 of a millimeter. Okay, I don't want to send you off on a wild goose chase. Your time is valuable, just like mine. I would direct you to the work of Sherrard and co-authors. And let me just see if I've let's see what I've got. What have I got here? Yes. Let me take you to, for example, the work of, oh, can you see this? Sorry, am I sharing my screen with you? 1 second. Apologies. In fact, let me open up a couple for you here. I'll open up 2 or 3 and then I'll share my screen. Bear with me, please. Okay, let me share the screen. There we go. Jim Sherrard, an eminent practitioner in dam engineering, wrote a series of landmark papers in ASCE, basic properties of sand and gravel filters, and complemented that with filters for silts and clays, and complemented it. Probably this last, the third of them is not quite so critical, but I would encourage you to nonetheless take a look at it. The data sets are fantastic. Critical filters for impervious soils. So when an organization, so let's just go through this one more time again. This was 1984, but if you Google Jim Sherrard, it'll come up. I noticed that Lauren Dunnigan was teaching a webinar for I think it was either the USSD, the US Society in Dams, or American Society of Dam Safety Officials. But I noticed he was teaching a webinar about a year ago on filter design. But his collaboration with Sherrard and Talbot, but the long-standing Dunnigan and Sherrard collaboration really formalized the building blocks of modern design practice for filters, granular filters. So 1984, basic properties, 1984 again in ASCE, filters for silts and clays, and then the third one, the critical filters for impervious soils. That body of work collectively is the cornerstone of modern granular design, granular filter design practice in the Americas. Okay, so moving back to this screen share, that would be the literature. I'd say go take a look at that. If you have the interest professionally and you feel it's an investment in yourself, by all means, pursue other complementary work. Sometimes it's neat to do a citation search for Sherrard and see who's been quoting his work and maybe seeking to add to it. But that's the intent. And let me park now this point and this learning objective of assuring ourselves that empirical rules that we're using for filter design are applicable. And if I was, yeah, okay, so I'll hold on that. Let us move now. So now our interest is in the geotextile filters. And culturally, we're on the lookout for where are design criteria. They're going to be empirical. Where are these design criteria coming from? How are they being expressed? And also, what kind of change or evolution do we see? Because if we can understand where current practice has evolved from, it gives us that little greater notch of confidence, don't you think, in terms of applying it? So, moving on, let me start with the Canadian Foundation Engineering Manual. There are two chapters, one on reinforced soil, one on geosynthetics more generally and their material properties. And in this regard, we covered off. I want to get to the next page, but we've noted on the way through that we're interested in the porosity of a non-woven geotextile. It's not going to be it exerts a strong influence, but it's not a kind of a key criterion. It's almost there may be some applications that simply require a certain porosity of a non-woven geotextile, but we'll acknowledge that. And in the same way, the porosity of a non-woven geotextile, we may on occasion see the percent open area for a woven geotextile. Ways of characterizing, I'd almost call it the architecture of the material. Let me see if I can, here is a woven geotextile, and very quickly we can just acknowledge, do you see, I need to get rid of the shadow, but do you see, it's like a quasi tennis racket with its warp and its weft, and that produces a percent open area, because you can just see right through the thing. Okay, so that's our, what is the percent open area? Is it 4%? Is it 5%? Is it 6%? And with the non-woven geotextile, it's the porosity. If I pull out one more time this material from Valcross, can you imagine it? It's got a three-dimensional. We can't see through it. There isn't a percent open area like there was for the woven, but rather we can look at the porosity, and you might say, gee, I wonder if the porosity changes if I squeeze it, and of course it does. So the porosity is going to be measured under a standard, and it's a very light seating stress, and an ASTM standard for that. Okay. And then we have an interest in the opening size, and we looked at how opening size is measured with dry sieving, and we get, let's stick with apparent opening size, or AOS. That would be our equivalent to the 095, that 95% of the openings are the same size or smaller. We take this as the characteristic pore size. The characteristic pore size of the geotextile, 095. There it is there, 095 refers to the opening size of the geotextile, for which 95% of the openings are the same size or smaller. So let's bundle all of this together. And that's really going to be the one that ties us into our base soil retention. This 095 is this 095 here. Before leaving this page, and it's again just bridging across from the last lecture, then there's the permeability of the hydraulic, or the permeability normal to the plane, cross-plane permeability of the geotextile. Although we noted that the permittivity is commonly quoted, so it's actually the permittivity normal to the plane that's normally quoted. Okay, and that was that units of seconds to the -1. So permittivity, 095, percent open area for a woven, which is almost a pre-qualifier. Porosity of a non-woven geotextile, pretty much a pre-qualifier. And we could go in and carry across this permittivity here and say that we would be looking at a permittivity. And if we cross the page of the Canadian Foundation Engineering Manual, there is that permittivity defined there. Okay. So moving on. What about the design? How is what kind of criteria are we going to use for the design part of it? Where do these empirical criteria come from? Well, the first distinction that we tend to make is whether or not our seepage regime is steady state flow, unidirectional flow in one direction, or whether, if we skip over the page, we have a case of dynamic, pulsating, or cyclic flow. So that's kind of interesting, and then that might cause us to go back and say, oh, what does my National Engineering Handbook have to say for granular filters? Is the base soil retention in the chapter 26, is that for unidirectional flow? And that begs the question, oh, if we go back to Sherrard's work, was that testing with unidirectional flow? Is that a constraint that is applying here? So what do we have in the Canadian Foundation Engineering Manual? Well, it makes a distinction between soils with less than 50% passing, the number 200 civ, less than 50% silt and clay size, as opposed to, and we have steady state flow, as opposed to soils with more than 50% passing, the number 200 civ. Okay. And the Canadian Foundation Engineering Manual has gone through a number of editions. This is extracted from the 4th edition. I must check. I should know it's because it's being revised at the moment. I'm not too sure what the status of the revision is. But there we have that our AOS, okay, which is 095. And that's a size in millimeters, must be less than something. Okay, fair enough. It's got to be less than some indicative measure of the grain size of the soil, perhaps manipulated by some empirical constant. Fair enough. The indicative particle size of the soil, up to and including a coefficient of uniformity of 8, it's D85. Okay, so no big surprise there. In fact, let's capture that. Is going to be D85, D85, D85. And it transpires that the little constant b is a function of the coefficient of uniformity. And if you look at the way these all work themselves through, it turns out that b is varying between 1 and 2. Okay, so basically we're saying the opening size of the geotextile for soils with a coefficient of uniformity less than 8 should be less than 1 to 2 times D85 of the soil. And the belief here is that the action of the soil retention is, let me capture it. Let me capture it in this image here. Okay. Can you imagine that this is the soil, this is the base soil. Now we've got various particle sizes from very coarse, you know, let's find the largest one, call it D100, let's call these guys D85. And you come along, let me get my my geotextile. And we come along and we put a non-woven geotextile there, right? There's a non-woven geotextile. There's let's call this an enlarged photo of the pore size architecture. And you see what we're doing? We're saying, listen, we want the largest opening size, or nearly the largest opening size, O95. Where is the 95th percentile opening size? And we want to make sure that that opening size is less than D85 of the soil. And the argument goes that if that's the case, we're going to get a little bit of washout of fines naturally. Let's call that a bridging network. So a little flushing out, but ultimately it starts to set itself up in a manner where arching of particles and bridging mechanisms kick in, and ultimately, and over a relatively short distance, you bridge your way back to an undisturbed soil, and it's you set up. I'm going to capture it as a phrase. Let's call it a stable pore architecture. And of course, with unidirectional flow, there's a very good chance that pore architecture could establish itself, and in the absence of any disturbance, probably sit there quite happily. Maybe if the demand was to change, that pore bridging architecture gets a little bit more, it's hunting for capacity to maintain its bridging architecture. And can you imagine if it switched to reversing flow? Excuse me, that might challenge things a little bit more. Thus, perhaps the empiricism, wherever it's come from, for unidirectional flow is captured like that. Okay, so that's very much the philosophy of the design, and bear with me one second. Were I to remind me to talk about a due date, please, before the end of this lecture for the assignment number 2. But if I go to Cedar Green's book, I don't know if I think I mentioned this earlier to you, but Cedar Green's book, absolutely fantastic book, Seepage, Drainage, and Flow Nets. If there isn't a copy of this in your office, go and make sure one is obtained. And if I go into here, bear with me while I turn. Look at this image, which is an image from Cedar Green for granular filters. He makes a couple of comments, ironically, way back then about geotextile filters. But here's the image of a granular filter. There's the D85 of the soil, the D15 of the filter. Now that's really a surrogate for an opening size. And look, here's soil which has migrated into the filter and is held by the D85 soil particles. So you start with one arrangement and you set up this filter interface. And it too will be based on this bridging pore architecture structure. Okay, so we say thank you to Cedar Green for that. Back on the bookshelf, and we now realize what is it? Is it a conceptual model? Is it a system? How the system is working? But this is what we're endeavoring to capture. And in the 4th edition, a fellow called Jean Lafleur took the lead on writing it, and Jean Lafleur advocated for soils that are more broadly graded. And now we're getting into the world of earth dams, and Jean Lafleur worked over the years with Hydro-Quebec on a number of dams. He was very good as a filter design, both granular and geotextile. And so he was advocating in 1999 that if you got soils greater than, or the coefficient of uniformity greater than 8, then okay, B is going to default to 1, but your indicative particle size is going to change. Change it to D50, change it to D30. concave upward gradation curves. They are potentially internally unstable. Gap-graded soils, potentially internally unstable. And again, if I interweave the lecture material with the homework assignment, in the second part, where I ask you to employ the USBR design standards, then I throw in an addition on the matter of soil retention criteria, and with reference to the laboratory test data of Jean Lafleur 1999, which is the same Jean Lafleur 1999, I ask you to take the lab test data from which Jean Lafleur elected to make up these empirical rules, and I get you to check them against Scott Lutich, and we'll hold for Scott Lutich in just a second. We're currently with current Canadian practice, but now we have to put it in a broader context. Okay. All of that for soils that are predominantly sandy gravel, less than 50% silt clay size. If the soil is finer, the base soil is finer, soils with more than 50% passing the number 200 CIV, then we end up with AOS shouldn't exceed 0.3 of a millimeter. 0.95 less than 0.3 of a millimeter. And again, we see parallels. In your own time, you two will have an opportunity to explore them. But we see parallels between AOS being less than 0.3 of a millimeter and D15 being less than 0.7 of a millimeter. Remember, D15 particle size, AOS opening size. So we see similar DNA, similar constructs to the empirical approaches in granular and geotextile filters. And that maybe shouldn't surprise us, because there's actually in the background a limited body of good quality lab data and a limited number of players on all of these projects that have driven them. Right? And it will be industry problems that have driven it. It was industry problems that drove Jim Sherrard's work. Right? So there we have. Where are we in the big picture? We've looked at base soil retention for geotextile filters. 0.95 or AOS must be less than a certain value. And there are our, oops, let me move this down a little bit. There are our criteria: soil retention, steady safe flow. Then in the Canadian Foundation Engineering Manual, just to wrap ourselves around Canadian practice, for permeability, some, I'd call it general motherhood statements of general consensus statements that we want the filter to be more permeable than the base soil. That can get tricky, by the way. If your base soil is quite coarse, that can get tricky. Trying to find something that is more permeable than a clean medium to coarse sand could be quite tricky. And I remember there was a very good field engineer. I hold her in the highest regard. She may well now be retired. She worked in the natural resources sector in British Columbia. Her name is Glynis Horrell. And I remember being out in the field with Glynis one day chatting about geotextile filters. And she said, you know, she came across a road stabilization where the contractor had put down geotextile all along a cut bank of soil. But in that cut bank of soil were a few locations where the soils were quite sandy. And she took a look at it and said, no, I can't accept this, and instructed the contractor to actually punch holes in the geotextile. If you're going to cover that with riprap rock, I want you to punch holes in it, because otherwise the geotextile that you're putting over top of these exposures, these lenses, interbedded lenses of sands, and some concentrated buried channels on these forested hill slopes, odds on that geotextile is going to cap impede the flow. And she'd seen enough washouts in her time to recommend changing it. Over the page here, then for the permeability criteria, right, if we carry those over here, for the permeability criteria, basically, were we to follow an index test, permittivity, the permittivity's got to be greater than a certain value, depending on the percentage fines. 15% passing, 15 to 50, greater than 50% passing. And as the hydraulic conductivity of the material diminishes, so the expectations for the permittivity diminishes. And if you like, that's parking Canadian practice with permittivity must be greater than or equal to some value. And that leaves us with one last part. That's the tensile strength for Canadian practice, and then we'll put Canadian practice in context so that we're not working in isolation here. Actually, let me pause just to acknowledge a few other, I think, quite elegant little statements. Arguably, at the moment, we've said that the opening size must be smaller than some function of D85. The opening size must be smaller. On the other hand, we don't want the opening size necessarily to be too small, right? And even though that's going to be captured to a certain extent with the permeability, if we have concern for clogging, and the easiest way to clog a geotextile is to put it against in the absence of biochemical influences, the easiest way to physically clog a geotextile is to put it against a gap-graded soil. Do you remember from our last lecture? We looked at that a little bit. And so this is where, if you have concerns for filter compatibility, you know, I might almost say this is not a bad idea to check to see whether the opening size is greater than 3 times D15 of the soil. But in reality, if you've really got concerns that the geotextile may not be filter compatible, you might be looking at running either a gradient ratio test or a hydraulic conductivity ratio test. There are some, I'd call it practical comments here in terms of ensuring a very good contact between the geotextile and the base soil. That's a little easier to achieve with a granular filter, because obviously it's just going to, you know, lay down over the surface. The geotextile, because it's got tensile strength, can you imagine if your base soil is trimmed and prepped, but perhaps it's got undulations and so on, and you place the geotextile over the ground, the base soil, and the geotextile slightly in tension and being stretched, maybe the geotextile could stretch across a little bit like the surface of a drum. It could stretch across and actually not be in decent contact with the base soil, not in full intimate contact with the base soil. So there's a couple of comments related to that in there. And then the argument is made for dynamic pulsing, reversing flow, a little bit more demanding, maybe the AOS should be reduced in size. If you remember in the previous page, basically for anything with a coefficient of uniformity, let's say at least up to 8, just for simplicity of comparison, AOS is going to be less than 1 to 2 times D85, and for steady state. And for reversing flow, AOS is going to be less than 0.5 times D85. If you like, that constant of the previous page, that would be the equivalent to the B of the previous page, and this would be equivalent to the indicative particle size. of the previous page. And it begs the question, where does this come from? The answer is very limited lab testing, to tell you the truth. In the same way that for granular filters, if you hunt around and find an empirical design criterion for a granular filter, it's going to be from very limited lab testing. So, Canadian practice, does that pretty much cover it? Yes, it does. Interim summary before we move on to place Canadian context of today in the evolution of practice in general, in this empiricism. We have selection criteria for base soil retention, permeability, and tensile strength. In the lecture so far, we've looked at Canadian practice for base soil retention and Canadian practice for permeability. We'll come to tensile strength shortly. Let's broaden our appreciation for the nature and origins of retention criteria for geotextiles. I had the privilege of working with a long-standing friend, Brazilian friend, Enio Palmeira. We did our PhDs together many, many years ago, and then Enio returned to his home country of Brazil, and I emigrated to Canada via Norway, a couple of years in Norway, and then we were invited to pull together. I think it was a lecture somewhere, and invited to pull together a synthesis of design practice. Quite instructive in the U.S. 1972. So you know what's that? Only 50 years ago? Is that pretty much getting close to it? And we have O95, D85 remarks as to what they're intended for. OJINK in the Netherlands, not O95, O90, different index test, not D85, D90, different indicative size. But hey, I want to cruise through here for just a couple of examples. And in so doing, the learning, not objective, but maybe the appreciation is, look at that. We go back considerable time for empirical design criteria and over a number of countries, US, Netherlands, US, Army Corps of Engineers, Giroux was intimately involved in the Valcross Dam, French criteria. There we see coefficient of uniformity coming in. I think culturally, that influence may also have extended to Jean Lafleur and his considerations. Hirten, Germany, Carroll, US, Barry Christopher, and Bob Holtz, retained by US Federal Highways. And we see a pattern, okay? We've got that the opening size, whichever index test you make, it must be less than some measure of the soil, given an indicative particle size of the soil, maybe taking into consideration coefficient of uniformities and so on. French committees on geotextiles. Now we see committees formalizing the work of individuals. Lawson was Hong Kong. Greg Fisher in the US, a PhD with Bob Holtz. Maracci in Italy, the UK. Jean Lafleur, there's the Jean Lafleur, 1999. Jacek Milnerek. I'll make a couple of comments about, I think his work is quite interesting, actually. But my point is, 2003, I can't remember which country this was. And look at that, Giroux still working on it, 2010. So, you know, one point to note is Giroux in 1982, and then Giroux in 2010. And so we can acknowledge perhaps that empiricism, it varies a little bit, it doesn't change radically, but you know, it evolves, little tweaks to it, new data sets that come out, new perspectives and things get tweaked a little bit. And that's the point that I wanted to convey to you through this overview. We see work, including the work of Lafleur, that has strongly influenced Canadian practice for broadly graded soils, coefficient of uniformity greater than 8. But if we look at the Barry Christopher and Bob Holtz, this US federal highways work, O95 divided by D85 less than 1 to 2. That, in essence, is the O95. So we can go in here and say this is strongly influenced, and we'll highlight it. Christopher and Holtz. Strong influence on Canadian practice. Let's go in there and put Barry Christopher and Bob Holtz. I think that was, 1985. That was highways sponsored kinds of applications. And then Jean Lafleur, let's highlight Jean Lafleur, 1999. Okay. I'm also going to highlight this, Scott Lutich with design charts. And then the last that I'm going to highlight is Jacek Milnerek with design charts. Okay. And I do this because if we acknowledge that this has strongly influenced the Canadian Foundation Engineering Manual, and this body of work has strongly influenced the Canadian Foundation Engineering Manual, I think it's worth knowing about this work, and I think it's worth knowing about Scott Lutich's work. So let's just take a little moment now to reflect on those design charts. And I'll start with Scott Lutich. Scott Lutich. When I speak to Lutich et al., it's this geotextile filter design. It was published in Geotextiles and Geomembranes, 1992. And in fact, it also appears, bear with me so I can pull it up. It appears not only in that journal article, which was where they formalized it, but this Geosyntec consultants essentially got a contract to develop the design guidance. They published it in a journal, but they also it also got introduced into the sponsoring company's design literature. If you like, the manufacturer had pretty well just contracted with a consulting engineer, not just any consulting engineer, because Giroux, who also had his design guides, his design rules, and Giroux, who had been involved way back early, even in the Valcross Dam, and then went on to be one of the original founders of Geosyntec consultants, who hoovered up an awful lot of geosynthetics consulting in the US and internationally. But it's interesting how that, do you see how the players, the number of individual players is relatively finite. But they produced this design chart. Let me, there we go. It's a pretty ropey version of it produced here, but it does appear also in the Geotextiles and Geomembranes article. But basically, you know, look at this: soil retention criteria for steady state flow, soil retention criteria for dynamic flow. And in essence, depending on the nature of the soil, the base soil, you start to categorize the base soil by type. And depending on the base soil category by type, you start floating out into empirical rules. And you know, it's a chart that it doesn't map onto the way in which we design granular filters. You know, kind of, it doesn't map directly on top, but philosophically, you're doing something similar. You're categorizing the base soil. Then you're going to have in the background bodies of test data that you may be familiar with, and you match empirical rules to it. So I quite like that. In fact, I've used it on projects, including a case study that we'll go take a look at shortly. So that's what I wanted to say about the Lutic work. And again, without sounding like a broken record on this assignment number 2. On the matter of the soil retention criteria, and with reference to the lab test data of Lafleur, take those lab test data, but evaluate the design guide of Lutic et al. And comment upon the conservatism or otherwise of the design guide. And the references are down at the bottom here. Okay, so I'm really trying to integrate your appreciation for the evolution of design guidance, the variety that exists, which is perhaps arguably a strength of the geosynthetics design guidance, the variety that we see here, but then to have some basis to develop, by virtue of the homework design assignment, to develop some basis of having a gut feel. You know what I mean? A gut feel for what you're doing, rather than just blindly applying empirical rules. No. We don't want to be doing that. That would be that would not be an appropriate standard of practice to be conveying to you. Okay. So that was Scott Lutic's work. And to tell you the truth, Scott Lutic was quite instrumental in pushing, and Geosynthetics was the hydraulic conductivity ratio test, for example. And then finally, I wanted to acknowledge, because I think it's quite elegant actually, Jacek Milnerek. He's retired now. What a super guy. Did a agricultural sciences degree in Poland. Emigrated from Poland long before the Berlin Wall came down and all of that kind of, you know, everyone's super friendly in Europe now, moderately so. But Jacek emigrated to Canada, did a PhD at École Polytechnique. Not with Jean Lafleur, but he had, there was another colleague there. What was, name escapes me. Anyway, and then Jacek went into the private sector and worked in a testing lab, geosynthetics testing lab, and then rose to be a director of the company, actually. He is a super, super nice and super accomplished individual. And Jacek, about 2000, would it have been? Yeah, 2000. Jacek produced these design charts, and I've copied one of them. He produced a design chart for unidirectional flow and a design chart for reversing flow. This is the unidirectional flow. What I liked about this is, and let me just get to it. Look, you end up with a filtration test of the selected system is recommended, right? You end up with a filtration test of the selected system is recommended. And what I liked about that was that it was recognizing that there are shortcomings to empiricism, and it may not be appropriate for all base soil combinations simply to rely on an empirical rule derived from a bunch of laboratory tests. And to tell you the truth, keep an eye out for the following. When you go to Jean Lafleur's test data, take a look at the size of the test specimen and ask yourself if you're fully comfortable with the size of the test specimen. So culturally, that's what I wanted to get across from Jean Lafleur's work, that sets it up very nicely and does something a little bit like Scott Lutage. You're kind of following different categories of soil type by grain size, by plasticity index, by finer fraction content. It's all focused on FOS, the filtration opening size. And we could make perhaps the little note here that FOS, the filtration opening size, it's obtained by hydrodynamic sieving. And the FOS test, it was a Canadian General Standards Board CGSB test, and it's now been rescinded. I'm not quite too sure why. But we could argue that the FOS by that test method is approximately equivalent to the AOS. Where I in design practice, I might run through this to inform myself using the FOS and the AOS interchangeably, but I would know that that was a caveat. But I like the elegance. I think it'll challenge you to think about a couple of things if you were to run through on this. Okay. Now, in moving to close on the soil retention, I thought to share with you some test data. And by looking at these test data, it's going to inform a little bit the way in which which you might look at the Jean Lafleur test data as well. So let me take you to a body of work. It was done by Rashmi Hawley. She was a super nice individual. Did her master. I think her undergraduate was from University of New Brunswick. Did her master's here, and then returned to New Brunswick Maritimes. And last I heard from her, she was with Jake Whitford, but that was some time ago. Anyway, we had a very enjoyable industry-sponsored master's thesis, and in it she did rigid wall permeameter testing. In essence, what she did was to take a geotextile, in fact, a number of geotextiles. In fact, that number was 1, 2, 3, 4, 5, 6, 7 different types of geotextiles. So let's put the geotextile in here. Please note, 2 of them are non-woven, and 1, 2, 3, 4, 5 are woven geotextiles. Perhaps we'll make that distinction. These are non-woven, and these are woven. So I'll make that distinction there. Woven and non-woven. So those geotextiles were placed at the base of the permeameter. And then soil reconstituted on top of it. And the soil reconstituted on top of it the soil specimen. Three types of soils. Here is the soil. The first soil was a relatively benign Fraser River sand. The second soil was a mine waste tailings. And the third soil was a problematic silty sand from Port Coquitlam, so a suburb of Vancouver, and it's always been a little bit of a challenging material for filter design. And so this was a university industry sponsored project, and so it was very much practice oriented. So the soil times 3, okay? So that leads to a 7x3 matrix. There are the 3 soils. Let's look at the soils. The mine waste tailings, the Port Coquitlam, silty sand, and the combinations informed by, for example, the D85 of those soils, and informed by the apparent opening size, or O95, of the geotextiles, we end up with a ratio AOS to D85. And that's pretty much, if we go back to the Canadian Foundation Engineering Manual, the ratio in brackets AOS over D85 is pretty much AOS divided by D85. So Canadian Foundation Engineering practices say AOS over D85 should be less than 1 to 2 to provide for soil retention. And what Rashmi explored then was, well, let's look at those AOS over D85 ratios. The lowest is about 0.6, and with the Fraser River sand opening up as far as 1.8. The mine waste tailings is as low as 0.7 and opening up to a ratio of 2.1. And the Port Coquitlam silty sand is a ratio of 1 and opening up to a value of 2.8. So it's kind of, and the experiment was designed to look at this range. So in the bottom now, we're able to plot data from testing where Rashmi put a relatively low surcharge pressure on the soil of 25 kPa. Many filtration applications. Let's look at highways and slope stabilization, relatively low pressure, and ran a hydraulic gradient, so ran seepage flow, unidirectional seepage flow down through the soil and across the geotextile at a hydraulic gradient of 4. For 90 minutes. So a nominally aggressive, but not super aggressive gradient for a relatively short period of time. And what we discover is that if you're going to have filter incompatibility, it tends to manifest itself relatively quickly. And so in reconstituting the soil on top of the geotextile, she was able to distinguish in her testing between soil, summary of mass of soil passing through the geotextile during specimen reconstitution, including an enormously high value. In fact, it proved impossible to reconstitute that test specimen, so the test was not performed. not be formed because basically the soil, this combination of P570, the P570 with the Port Coquitlam, or sorry, the 570 with the Port Coquitlam sand, the P570 combination with the very, very large opening size, the soil just fell through the geotextile. So that didn't even get done. But she was able to distinguish between soil loss during specimen reconstitution and soil loss as a consequence of unidirectional flow. And thus, the mass of soil lost, grams per meter squared, can be plotted against the opening size, non-dimensionalized by D85. If that's even a little bit grainy on yours, let's acknowledge that this is AOS over D85. That's the value in parenthesis here. And this is the mass of soil lost. That's coming from here. That would be this column over here. And an earlier version than the current version, but I don't think it's changed. So this is the Canadian Geotechnical Society. It's the Foundation Engineering Manual 1992. This was basically, it's the Christopher and Holtz. It would say that for the Fraser River sand, right? This would be the Fraser River sand, that AOS over D85 should be less than 1 for Fraser River sand. For the Port Coquitlam silty sand, AOS over D85 should be less than 1.7. So the Port Coquitlam, I think it's a little bit lost here. Let me sketch it in let me sketch it in here. And let me sketch it in here. So the Port Coquitlam PCS would have an AOS over D85 less than 1.4. And the mine waste tailings, the Foundation Engineering Manual will call for an AOS over D85 less than 1.7. And what we have are data for the mass loss as you open it up. And what we see there for the Fraser River sand, the dark diamonds, you can open it up, and for that uniformly graded sand, the way the bridging and pore architecture, you can open it up as large as 1.8. Let me bring that down. You can open it up to an AOS of a D85 of 1.8 and still no mass loss, even though the design criterion would have a B constant of 1. So clearly conservative. If we look at the Port Coquitlam silty sand, the design guide says AOS over D85 should be less than 1.4. And the mass loss, as we go through from 1 through 1.4 to 2, and there's the mass loss. We can see the mass loss here. Turns out to be of the order of maybe 50 to 100 grams per meter squared. Not a very significant amount of material. And likewise, and thus it would appear there's a degree of conservatism, and the Canadian Foundation Engineering Manual criterion appears reasonable. And for the mine waste tailings with a ratio less than 1.7, and those would be the triangular data, and there are the triangular data there. Once again, no evidence of catastrophic piping. In fact, the catastrophic piping was evident when the opening size of the woven material opened up as large as 2.8. So, you know, we could, if we wanted to, take this insight of not being able to reconstitute the specimen, this combination of 2.8, and we could go to an AOS over D85 2.8. Let's go in here. And I'm going to take this combination, which is associated with not being able to reconstitute the test specimen because of the geotextile being so open. And I could take that down to here and argue that this circle for the PCS material, but I end up with an enormous value here. So we see a couple of truisms here. Number one, how much conservatism is there in design practice? And you can exceed it relatively comfortably, but there will be a threshold where when you hit, especially for a woven geotextile, when you hit material piping through it, your geotextile is so open as a woven material that the soil will just continue to pass through. So that we recognize a sensitivity. The design practice is conservative, the empiricism is conservative, but there's an enormous sensitivity to the it opening up too much. Okay. If we capture all of that and we look back on the Canadian design practice, soils with a coefficient of uniformity of 1.8, a coefficient of uniformity of 3.3, and a coefficient of uniformity of 5.8. And we map that on to the empiricism of the Fraser River sand at 1.8, the mine waste tailings at 3.3, and the Port Coquitlam material at 5.8. It all leads us to believe that that Canadian practice is consistent with the body of data, for example, that Rashmi generated in these laboratory tests. And that's the origin of empiricism, okay? Now, for the next bit, going beyond this, this was post-dated Rashmi's work, and Jean Lafleur proposed this. Yeah, take a look at it and see how comfortable you are with the nature of some of those data. And you might be pleasantly or you might be unpleasantly surprised, but I leave that for a path of discovery on that assignment. Now, moving on, we have, I hope, addressed the matter of geotextile filter design, base soil retention. We've looked at Canadian practice. We've put that in the context of a bunch of other empirical rules from around the world and over a considerable period of time. And then we've swept through to look at lab test data acquired with the elegance and rigor that a master's thesis produces. And for the range of materials tested, Fraser River sand, mine waste, and this PCS, we find those empirical criteria to be good. Moving on to permeability, I don't have so much to say there. I'm going to wrap it into the case study we'll look at shortly. There is the option to say, listen, the permittivity should be greater than a certain amount. There's the option to look at the normal permeability being greater than that of the base soil. But to tell you the truth, I would come back to the Jacek-Mielnarek observation that if you have any concern for permeability and soil retention in combination, test the material. And I'll illustrate that for the Alouette Dam project. So really, I don't have too much to say about permeability. The proof comes from running a filter compatibility test, such as gradient ratio or hydraulic conductivity ratio, okay? And I can pretty much cover off and I'm going to do it a little bit collectively. What about the matter of tensile strength? The Canadian Foundation Engineering Manual. We really want the geotextile to be strong enough to survive installation, and together with any polymer additives that, for example, for UV stabilization, to be durable over the service life of the structure. And this installation and avoiding punching holes in it and inadvertently damaging it, I'd say the analogy would be a little bit like the granular filter not suffering grain crushing and generating adverse fines. That would be my analogous comment. And pretty much everyone defaults in terms of adequate strength to the AASHTO. So this is really a highways approach, the AASHTO designation. You can choose one of 3 strength classes. Very strong, moderately strong, those would be very much. The puncture strength test has evolved over time, currently 6241. But these are, in essence, 3 index tests for strength. And recall the manufacturers understanding all of this now will almost inform you of which AASHTO strength classification any particular product line or product within a product line holds. And I'm fairly confident with this, and I'll tell you why. And this was a neat little assignment that kept me and a co-op student honest one summer. I got engaged by the forest sector in British Columbia to advise on geotextile applications in forest engineering. And for that, myself and a co-op student went out and we visited a bunch of roads, a bunch of log culverts and cut slopes and subdrains and channel and bank stabilization and all the way through to a bridge abutment. And we went and visited. Let me see. I mean, we did a bunch of case reports, chasing around the far-flung regions of British Columbia. It was a lot of fun as a young academic, kept me very honest. And we went out to these sites and we looked at the roads. We looked at the grab and the puncture and the tear strength of the materials that were used. We looked at the permittivities, the AOS. We went into the construction records, the materials that were purchased. And then we looked at whether or not the geotextile met the class 1, class 2. And we did that there. And we did it here and looked at it and got the material properties and looked at the applications. And this is a geogrid. And log culverts, where you're stretching the geotextile over the log culvert, and then end dumping and kind of, I mean, pretty aggressive. And we're not talking about, tight engineering supervision. This is resource access roads. And again, oops, my bad with the. We looked at the grab and the puncture and the tear strength and the permittivity, and we looked at how it was done, and we checked it with the AASHTO specification. This is a little bit like the situation with Glynis Horrell, who was concerned to make sure you've got good cross-plane permeability. And applications where you've got cut slope stabilization, and again, what was the grab strength? You've got to be careful of these seeps and so on. And long story short, everything that we captured in that little book, even produced it on waterproof paper and with a little, it's intended to be on the back of a pickup truck, basically. Okay, just. go at it. But everything that we did in that resource engineering sector, and man, did I respect the gut feel of many of those people that I interfaced with, is it's all good, right? If you're looking at AASHTO and you're looking at strength, AASHTO will say for permanent erosion control, the requirements are for riprap stone, basic function is filtration with some separation, don't use woven slip films. They're too slippy. The rock doesn't adhere to them quite so well. But my main point was go in and you know, get a class 1 or a class 2. And what you're doing is blindly applying a kind of almost a standard specification document. And I can tell you quite emphatically from all of those case studies in the forest sector, for all those roads and log culverts and cut slopes and bank stabilizations, I can tell you that this works. So that's where our strength would come from. Okay, so if I sweep back through and now we're moving towards closure. We see criteria for base soil retention. We see criteria for permeability. And for criteria on strength, I would defer you to the American Association of State Highway and Transportation Officials, that AASHTO M288, which is brought over into the Canadian Foundation Engineering Manual, strength classes. Times 3 different strength classes. Okay, so in advance of turning to this case study, let me ask you if there are any questions of clarification. I appreciate I haven't sent you into a breakout group, and you may be wondering if you know how long do you have to listen to this for? But are there any questions of clarification or anything that arises as a consequence of some of your experience and practice? Any questions that you would like to raise? I'd be only too delighted to answer them.
Just a question on some of that lab testing. We're looking at the percentage of the mass lost. What is like an acceptable sort of criteria in terms of having some mass loss?
Yes.
Because I know not everything's going to be in a perfect world where we have 100% is retained. So
yeah. So I can give you 2 sources to go for that, and I wouldn't say blindly apply them. Source number 1 would be that Jean Lafleur. Now, I can't remember if it was in his 1999 document, and I'd have to go back and check the absolute number, but he said that if you have of the order of about 1 kilogram or more per meter squared, of the order of 1,000 grams per meter squared, that's getting to be a large mass loss. His basis for that, I have no idea. Okay, but if I step one, so let's say way larger than what we're seeing here. In other words, these 50 grams per meter squared, which is really just a very tiny chocolate bar, or 30 grams per meter squared. 30 grams is inconsequential. let's go find something that weighs 50 grams and look at it and ask if we could have that come through a meter squared. That presupposes that your drain is not going to overly clog, and this is where there isn't an exact answer to it. But by way of a benchmark, and I think the number is probably too high, Jean Lafleur had said, listen, I start to get worried if it's more than about a kilogram per meter squared. And I'm sensitive to this, and in fact, I'll give you another heads up on the homework assignment. Contrast the basis for evaluation of a granular filter with that of a geotextile filter. The granular filter and the basis for evaluation of Foster and Fell is absolute mass of the soil. Is it more or is it less than 100 grams? One thing that I am attracted to by Jean Lafleur's approach is at least it's a mass per unit area. But Foster and Fell offer some numbers, at least for the size of permeameter testing they were doing. And you could look at those 100 grams per their surface area and equate it to grams per meter squared. I suspect it's going to be nudging quite high as well. So that's not quite, Ryan, that's not quite a straight closed form solution to your inquiry, but it's the context in which I would myself consider, does a number look relatively large or relatively small? Personally, yeah. I would do it with respect to those two. And I don't know of anybody else that's written on it. And I know that I was genuinely surprised by two things here: how relatively low the numbers were, and then if you really messed up on your soil retention, how very large they came very quickly. Witness the inability to even reconstitute the specimen.
Yeah, exactly.
Yeah. Okay. Any other questions now or? Okay. So listen, I'm going to work my way through the case study. I'm not going to read what's written here. I'm going to give you I'll call it the human story. You can read it in your own time. But in advance of doing that, let me acknowledge two things. One is in Canada next week, Wednesday is the 11th of November, and that is a statutory holiday in Canada. So for those of you outside of Canada, and for whom it may not be a statutory holiday, there is no lecture next week. Okay, so please make a note of that. I'll reiterate it in an email out. So that's housekeeping point number one. And then housekeeping point number two, when is the assignment going to be due? And I'm trying to think of what's fair and reasonable here. And this is what I came up with, okay? And it's informed by the following. Homework assignment number 2 you're doing, and there's the third of the 3 discussion exercises, which I will give out on the date of lecture number 10. Lecture number 10 will be the 18th of November, and that submission would be due for lecture 11, which will be the 25th of November. So this is due on the 25th of November, and that will inform that lecture. So that's a drop-dead deadline. Okay, 25th of November is that discussion exercise is due. So what I propose for assignment number 2 is you can choose your hand-in date. Work around other commitments that you've got. My only request is that you hand it in before the end of term. And the last lecture is the 2nd of December. So you choose your hand-in date, 2nd on or before the 2nd of December. okay? But I'm going to ask each of you to drop me an email and tell me what your hand-in date is going to be. And that'll help people, maybe just discipline themselves a little bit to it. So I think that's a kind of a self-determination approach for that assignment. And once again, I'll put that in the same email as the one with regard to no lecture on the 11th of November. Okay. So that's the method behind the madness, and I hope it appears reasonable. Now, let me tell you the human story about Alouette Dam. I alluded in the last lecture to the fact that, and this is the image I created, that the old spillway had erosion underneath the concrete slabs where they were placed in direct contact with the ground. Thus, the concept was to put an underdrain, which required a filter to the underdrain beneath the new spillway, but where the sides of the spillway were relatively steep in some sections, it would not be possible to put a granular filter and rock drain, which were the default target zones for the dam owner, and thus we were exploring the alternative of a geotextile filter and a geosynthetic drainage panel. Okay, that's the business case. There's a little history of the Alouette Dam here. That's very interesting. And then it describes the business case for rehabilitating the spillway. Now, the specification of the geotextile. Okay. Primary function, filtration. So we've got to specify a geotextile filter. All right. And we have some grain size information from boreholes, grain size analysis on samples retrieved from boreholes. It's a sandy silt, and are actually probably quite similar to some of the Port Coquitlam area. Medium grain size between 10 and 50 microns, so that's quite small. And then this very large range in D85. So that was the first challenge that I was working with was, wow, am I going to design a geotextile filter for a D85 of 40 microns, or am I going to do it for 0.6 of a millimeter? That's an enormous range. And a coefficient of uniformity of 20. This was before Jean Lafleur's amendments to the Canadian Foundation Engineering Manual. This predated Scott Lutich's design charts. This predated Jacek Milnerek's design charts. So we were really feeling our way into this. In fact, when I first got engaged with hydro, the question was, do you think we can use a geotextile? And it's a low plasticity material. So in fact, it's a horribly erodible, non-plastic sandy silt. Not a nice material to try and come up with a filter for it. And the arrangement that was conceived was to have the geotextile here in red, a prefabricated plastic geosynthetic cuspated drainage panel, and then cast the concrete panels on top of that. So the interest was in unidirectional flow of seeps in the base soil, and the filters primarily keeping the drain free, so that where we have any cracks or joints in the spillway panels, that water can be drained in a cuspated drain that is not compromised by piping of base soil into it. Okay, that's basically what we had to do. And so BC Hydro, the owners, said, well, first up, we have to we have to characterize the opening size of the soil, and we did that with regard to FOS. The manufacturers could provide us with the AOS value, but basically we got the pore size opening of the geotextile. We got FOS, and actually the owner paid for that testing to be done. Then we could obtain AOS values from technical literature, but we couldn't get FOS values. The manufacturers didn't have those. I think we did it for 3 materials because BC Hydro didn't want a sole source, so we had to kind of pre-qualify, I think it was 3 geotextiles. And the 3 non-wovens that we looked at all had an opening size of about 70 microns. But we knew the D85 was between 40 and 600 microns. So now, and this was about the tightest geotextile we could find commercially, right? This is at the really tight end of the non-woven geotextile market. And thus, we were compelled to do gradient ratio testing. It must have been standardized by that time, but the hydraulic conductivity ratio wasn't standardized as an ASTM test. It was just described in a Geotextiles and Geomembranes Journal article. And the testing was done in the US, actually at Geosyntex labs, and Scott Lutich was the guy that did the testing, right? If I remember the timing of the project, it was before Scott Lutich might have been before Scott Lutich had even published his design charts. And because this 095 was that little bit larger than the finer end of the D85 range, off we shipped the soils to Atlanta, Georgia, with the coupons of the geotextiles, and Geosyntec Inc. did the lab testing. And the question was, is it or is it not filter compatible based on these 2 tests, right? It's a little bit like the homework assignment, and I ask you, contrast the basis for evaluation of a granular filter with that of a geotextile filter. There's the gradient ratio test, there's the hydraulic conductivity ratio test, and that's actually what we did on the project. A significant finding of Geosyntec's work was the absence of any piping of soil. That was our big concern, that this non-plastic soil, if it was filter incompatible, we would have piping through the geotextile. And neither the gradient ratio or the hydraulic conductivity ratio testing revealed that. And we had conference calls down with Geosyntec Inc. and they produced a report out of their lab confirming that. It also demonstrated that the 3 candidate geotextiles that we'd sent down there were all giving a similar performance. And we were encouraged by that as well, because it gave us a sense of repeatability in the material's behavior. And because the hydraulic conductivity ratio test was originally intended for relatively lower permeability soils, and our soil was a bit like that, we placed a little bit more emphasis on the HCR test results in terms of our confidence building. But it was nice to have both of them. It was nice that the owner, BC Hydro, paid for a full suite of tests, right? You know, you recommend it, but you know, you want to make sure the client is on board for it. So in the end, the geotextile was required to have an opening size between 40 and 75 microns. That's what the contractor had to find and bid. Requirements for material strength, permittivity, UV degradation were established with reference to routine design guidance at that time. That would have, to tell you the truth, that would have been AASHTO's M288 approach. And they would be in general conformance with an AASHTO Class 2, not the strongest, the mid-strength material. We didn't feel that we needed a super strong material given the amount of engineering preparation and engineering supervision of construction, and we weren't dropping riprap on it, all that sort of thing. And the attributes of the geotextiles that had been tested and found acceptable, then those attributes were put in the specification document, and the contractor was invited to either source one of those three, and they wouldn't have to pay for any more testing, or to source an alternative to those three, but then they would have to do the suite of tests at their expense, and nobody elected to go that way. It's always a good idea to have the contractor submit in advance examples of the materials. If you want to manage the risk, that you're not caught by surprise, or the contractor shows up with some material, you look at it and you wonder, what the heck is that? This commitment to providing material in advance, along with who's making it and what's the product name and things like that. All very good. And that's prior to ordering it, and then prior to installation, the manufacturer's got to submit everything as well. So no installation is going to happen before you, as the engineer, know exactly what product with what attributes are being used as the geotextile filter. And I've stayed in touch with Hydro for many and varied reasons over the years, and done a lot of work with them over the years, and there's performance monitoring, there's instrumentation under the spillway, and pore pressure measurements, piezometric measurements, and so on, and everything I hear is confirming that the geotextile sections, along with the other granular and rock filter sections, are all performing well, and the performance monitoring of the system would imply that the component of the system, that is the filters and under drains, is doing its job. So that's the story of Alouette Dam. And that's a story where, and I'll make it my closing comments, the filter and under drains, to the Alouette Dam, where's my, here we go. The filter and under drain to the Alouette Dam spillway has a combination of geotextile filters in some locations, the steeper slopes, and granular filter in other locations. To tell you the truth, the geotextile filter was employed where it was felt it wouldn't be possible to place a granular filter. In specifying the geotextile filter, we looked at empirical rules. I looked at a number for base soil retention. I didn't really, other than wanting a reasonably permeable material, I didn't place too much emphasis on an index value here. Rather, we defaulted to gradient ratio and hydraulic conductivity ratio testing to look at the soil geotextile compatibility in combination. And I spec'd a strength class that was a medium strength material. I am an advocate on projects such as this, where the consequences of failure are quite significant. I am an advocate of Jacek Milnerek's filtration test of the selected system is recommended. Wise words explicitly in this design chart. And I know that from data such as data like this, that when I look at empirical design rules, I have a good gut feeling for whether or not they strike me as reasonable. It helps to know the players and the people that have produced those design guides. And thus, in closing, for your second design assignment, I'm asking you to familiarize yourself sufficiently to be confident in soil retention for granular filters. Familiarize yourself to be sufficiently confident on geotextile filter design, including the origins for the granular and the geotextile filter design, the origins of the empirical rules. And then I